Hi everybody. Today we had a live lecture and there was some technical difficulties, so it did not get recorded, surprisingly to me. So what I'm gonna do now is I'm gonna try to recreate a copy of the live lecture I gave today, except that the lecture was very kind of interactive, and today here I'm just gonna try to just lecture, but then there's going to be some place where I'm going to stop a little bit, and then I'm going to ask a question, so you can kind of pause the video and try to think about the question if you're watching this for the first time, as if you were in the Zoom session today. So let me first remind you what I did in the previous lecture. I was summarizing examples of cluster algebras, and so there were several examples, but they all have the following common features. So there were many things in common, but some things were different. So the common ones were that we have clusters, frozen variables, and extended clusters, and then all the clusters were on the same size. And then there was these clusters were they came together with some combinatorial data. So in the case of Grassmannian triangulations, this data was, it was triangulations for the Grassmannian 2n triangulations. And in the case of the flag variety, the combinatorial gadget was wiring diagrams. And then we had these exchange relations, which allow you to transform to get from one cluster to another one. Exchange relations. And so for the case of triangulations, these were P13, P24 is equal to whatever P12, P34 plus P14, P23. For wiring diagrams, this was P13, P2 was equal to P1, P23 plus P12, P3. These are relations between maximal minors of a matrix. These are relations between flag minors of a matrix. And so, but then the difficulty between these two examples was that for triangulations, you can flip any diagonal, but for wiring diagrams, some regions, some braid moves were allowed, but some were not allowed. And so that's the difference. And then, of course, besides these two examples, we also had the Selma sequence and freeze patterns. So you can ask, how do these examples, what's the common generalization of all these examples? And it has to be a common generalization. It has to have all these nice properties like Laurent, phenomenon, positivity. So today I'm going to define cluster algebras. Well, actually I'm not going to define those, but I'm going to define the machinery of cluster algebras. And so let me write down the topic: cluster algebras. And they were introduced in this paper by Fomin and Zelewinski. It's called Cluster Algebras 1 Foundations. And basically there they introduced this very general gadget, and then it got super popular because it was related to all these various fields. So, okay, let me try to start explaining cluster algebras. So the main combinatorial, every cluster algebra is assigned to a quiver. So let me first define a quiver. And well, what is a quiver? A quiver, it's basically a directed graph. So a quiver, Q is a directed graph, but it has to satisfy some very minor conditions. So it has to be without directed cycles of length 1 and 2. So here a directed cycle of length 1, it's basically a vertex with an arrow that points to itself, and this directed cycle of length 2 is a couple of vertices A and B with arrows from A to B and from B to A. So these two things are forbidden, but we're allowed to have everything else in a directed graph is basically allowed. So for example, you can have two vertices and multiple arrows from one vertex to another. That's okay. You can also have like a cycle of length more than 2. So for example, this is also okay. So the only two things that are not allowed are kind of self loops and these pairs of parallel arrows. Okay, now I'm also gonna be so far I have defined quivers, but remember we had these frozen variables, right? So there are usual variables that you can mutate, and there are also frozen variables. So I want to introduce the same for quivers, and that's going to be called an ice quiver. An ice quiver is a quiver together with some chosen some kind of fixed subset of what is called frozen vertices. So you just choose an arbitrary subset and declare those to be frozen, and everything else is mutable. So non-frozen vertices are called mutable. Okay, and now whenever you have a mutable vertex, you can mutate that vertex. And so now we come to the important definition of a quiver mutation. Quiver mutation. Well, so what we're going to do is we're going to choose a quiver. So let's say Q is a quiver. Let me actually show you the definition right here. So Q is a quiver, and K is choose some mutable vertex of your quiver Q. Well, Q is an ice quiver, let's say. And so what I'm going to do is I'm going to produce another quiver, which is going to be denoted by mu sub K of Q. It's going to be another quiver. So what's the combinatorial procedure? Well, it's a 3-step procedure. So the first step is kind of the most complicated one, and what we're going to do is for each path of length 2, right, so for each kind of 2 path, it goes I to K to J. So whenever you find an incoming arrow of K and an outgoing arrow from K, you create a shortcut. Which is just another edge. Create a shortcut from I to J. So whenever you see a pair of incoming outgoing arrows, then you create this kind of shortcut from I to J. That's going to be a new arrow in your quiver. Now the second step is you reverse all the arrows incident to k. So so that's pretty simple. You just kind of first you see this incoming and outgoing arrows, you create a shortcut, but then you reverse these arrows. I'm going to do an example later. And finally, the last step is you get some other oriented graph after the first two steps, but this oriented graph may not be a quiver. Right, so it is easy to check that you're not going to get any kind of cycles of length 1, but you may very easily get a directed cycle of length 2. So we're going to avoid that by just canceling all these opposite arrows. So remove all 2 cycles, which, so by 2 cycle, I mean a pair of opposite arrows. So you just cancel them, the order doesn't matter. You just find a 2 cycle, you remove these 2 arrows, and then you continue until there is no more 2 cycles. And so, okay, now I'm going to do an example. In class, this was an interactive example where people were telling me which vertices to mutate, but now I'm just going to recreate the same example. So the quiver looks like this, 1, 2, 3, 4, and then the arrows are, so there is a double arrow here, that's okay, and then, yeah, so that's the quiver on 4 vertices. Let's say all of them are mutable, and then what I'm going to do is I'm going to mutate the second vertex here. So I'm going to produce some new quiver, that's mu k of q, and so the question is, what is this quiver going to be? So if you're watching at home, I suggest you just kind of take this definition here, and then you just do it yourself. But I'm, of course, going to do it live as well. And so what I'm going to do is, if I mutate vertex 2, then first of all, the arrows, let me just redraw the arrows which are not connecting to, which are not incident to 2. So I have, again, I draw 1, 2, 3, 4, and then these 2 arrows I'm just going to preserve. But then, okay, so the first step is telling me that for each 2 path, so for each incoming arrow and for each outgoing arrow, I'm supposed to create a shortcut. So here I have 2 incoming arrows and 2 outgoing arrows, so that's, I'm going to create 4 shortcuts. 2 of them are going to go from 1 to 3, and 2 of them are going to go from 1 to 4. So let me try to do that in blue. 1 to 3, a double arrow from 1 to 3, and a double arrow from 1 to 4. And then, so that's step 1. And then step 2 is I'm going to have to reverse all the arrows that are incident to 2. So there is 4 arrows, and I'm just going to reverse their directions. I have 2 arrows here, and 1 here, and 1 here. And I am almost done. Right? There's this third step, which is I'm going to have to remove all possible 2 cycles. So there is, well, this quiver is almost all right, except that I have this 2 cycle. Or I also have these 2 arrows also form a 2 cycle. So I'm going to have to cancel one of these 2 cycles. What happens at step 3 is that, so step 3 is, let me copy the same quiver. Is I'm just going to remove, let's say, remove these 2 arrows, and I am done. So what I get is this quiver here, which is so this quiver is denoted by mu sub k of q. All right. So that's the example. Now let me try to mention some of the properties of the separation of quiver mutation. Properties of quiver mutation. And the first property, that's kind of the most important one, is that if you, so now okay, try to pause the video and think about what happens if I apply Quiver mutation twice at the same vertex. So I click on the vertex K and then click again. So what is it gonna be? And the answer is that Quiver mutation is an involution. So you're gonna get back to your original Quiver. So in other words, mu sub k is an involution. If you apply it twice, you get back to the same data. And so for example, I can now take this Quiver here and I can mutate the second vertex again, and I'm gonna get back to this Quiver. Like, that's actually a non-trivial exercise, so I encourage you to do this at home. In class they made me do this live and it was a little bit painful, but you can see it in the lecture notes. Now the second property is that the Quiver mutations commute. So they don't always commute, but they commute if the two vertices are not adjacent. So if Q has no arrows connecting I and J in either direction, then mu I commutes with mu J. That's also, well, all of these properties are not too hard to see, but I'm gonna leave their proof as an exercise for you to do at home. And finally, the third property is that, well, this is kind of a very trivial property, is that mutations commute, the operation of Quiver mutation commutes with arrow reversal. So proof, exercise. Okay, so now these are the properties, and these are all very nice, but now let me try to, because in our case we had not only just kind of triangulation, but we also have some algebraic data assigned to those triangulations, like the Splicker coordinates, you know, the matrix minors. And so let me try to slowly move into this algebraic direction. And first of all, let me fix the labeling of vertices of my Quiver. So I'm gonna label mutable vertices by 1, 2, up to n, and frozen vertices by n plus 1 all the way up to m. So my Quiver has m vertices, and then what I'm going to do is I'm going to label every vertex by a rational function. And that's going to be, so that's the definition of a seed. Definition, a seed is a pair x tilde comma q, where q is an I-squiver and x tilde is well, x tilde, let me write it down like this. X tilde is x1, x2 all the way up to xm, right? So is an assignment of some rational functions to the vertices of Q, mutable or frozen. And so here I'm being intentionally vague, so I'm saying some rational functions, but then let me just write down that I will clarify this later. I'm gonna require that these are algebraically independent and that they generate some ambient field. But so far, let's just assume these are some rational functions. And then with this data, I can define seed mutation. Okay, so definition, a seed mutation is the operation, well, basically you choose, so you choose a quiver, you choose a seed, x tilde, comma q, and a mutable vertex k of q. And then what you do with that data is you define mu sub k of x tilde, comma q, which is going to be some other seed. So it's going to be x tilde prime, q prime, where q prime is just, you just apply quiver mutation to q. So that's the same thing we did before. And x tilde prime is another family of rational functions, x1 prime all the way up to xm prime. So I'm only going to change one of these. So xi prime is going to be equal to either xi if I is not equal to k. Right, so I preserve all but one of these labels. But then the kth one changes non-trivially. So the recipe for that is it's going to be a subtraction-free expression of the following type. So in the denominator I'm going to have xk, and then in the numerator I'm going to have the product over all incoming arrows x sub I plus the product over all outgoing arrows x sub j divided by x sub k. And that's if I is equal to k. Right, so basically, yeah, I'm taking the product over all incoming neighbors with multiplicities. Right? So if I have like some I and then a bunch of arrows into k, then I'm gonna get xi squared times all the other incoming guys plus the product over all outgoing arrows. And that's seed mutation. So you get a new seed and then you can mutate some more and etc. So yeah, by the way, one thing I forgot to mention about quiver mutations, which I should have somewhere, yeah, it's somewhere here. So when you mutate a quiver, an ice quiver, it may happen that you introduce these arrows between frozen vertices. Right? I mean, if you have like a frozen vertex and then another one, and then an arrow like this and an arrow like this, and then if you mutate this vertex, then the rule tells you to introduce a shortcut, right? And so the shortcut is going to connect the frozen variables. And so what I want to say is that the arrows between frozen vertices, they don't matter. So the rule I'm going to use is that I'm always going to omit these, are always omitted. Whenever I see an arrow between two frozen vertices, I immediately am going to erase that arrow and then continue as if, yeah, you can leave them. Sometimes it's constructions are more beautiful if you leave these arrows, but in general, yeah, they don't matter. That's the point. I have just arbitrarily chosen to not draw them ever. Okay, now, all right, let me try to do some examples of seed mutation. So, for example, yeah, by the way, the product over, let's say, outgoing arrows is equal to 1 by convention if there are no outgoing arrows. So the product over an empty set is 1 as it usually is. And so let me try to do some example. So let's say I have a quiver with 2 mutable vertices, 1 and 2, and then it's labeled by x1 and x2. So I can start by mutating one of these vertices. And so let's say that's my quiver, and then let's say I mutate the second vertex. So I want to apply seed mutation to the second vertex. And so if you look at the definition of quiver mutation, there is no 2 path in this quiver. So the first step is trivial. I guess you don't see the first step. Yeah, the first step is trivial. And so the only step that matters is the second step, where I reverse all the arrows. And the quiver I'm going to get is going to look like this. And so by the seed mutation rule here, I'm not going to change x1. And so x1 stays the same, but x2 is going to change in a certain way. And so if I take the product over incoming arrows, I get x1. The other product is going to be empty, so it's equal to 1. And then I divide by x2. So x1 plus 1 over x2 is, so this is my new seed mu2 of this seed here. And then, okay, I can mutate again. Right? If I mutate at the second vertex again, I'm going to get back to my original quiver. But if I mutate at the first vertex, then I'm going to get something interesting. So mu1, I'm going to get the arrow is again going to reverse itself, and instead of x2, well, instead of this label, I'm gonna preserve it, so it's going to be the same, x1 plus 1 over 2. But then this label is going to be something interesting. And so what you're supposed to do is you're supposed to write x1 plus 1 over x2, right? That's the product over incoming arrows, plus the product over outgoing arrows divided by x1, and that's x1 plus x2 plus 1 over x1, x2, x1 plus x2 plus 1 over x1, x2. And these formulas, they may sound familiar to you. In one of the previous lectures, we have already seen this expression appear, and that's no coincidence. So if you look at the freeze pattern of order 3, I guess, or of order 5, no, then it has 4 rows, and so if you start with A and B, and then you propagate kind of to the right, then the entries are going to be like B plus 1 over A, and then this is going to be A plus B plus 1 over AB. So it's kind of very easy to see that the SL2 freeze pattern rule is giving you the same recurrence as this Quiver mutation here. So I'm gonna return to general freeze patterns, I guess, in the next lecture. But so far, let me try to do some other examples. So, well, what I want to do today is I want to completely understand the example of the Grassmannian 2, n, right? Remember, in this case, I choose some triangulation. T is a triangulation. And for example, I can draw a triangulation that okay, that's bad. All right. 1, 2, 3, 4, 5, 6. So I have this triangulation. And so then, remember, for the Grassmannian, we assigned like for every side and every diagonal had a certain minor attached to it. Like this minor was this corresponded to P13, and then this was P14, and etc. And so if you're watching this at home, what I encourage you to do is to just pause and try to guess what's the quiver, and what are its frozen vertices, mutable vertices, what are its edges, and what's the kind of, so okay, question is, what is the seed that corresponds to this triangulation here, which, so the condition is that it's supposed to evolve, like when you flip a triangulation, that's supposed to correspond to Quiver mutation, algebraically and combinatorially, right? So there's a certain rule you assign that produces a quiver out of a triangulation, such that as you flip an edge in a triangulation, the quiver gets mutated in a cluster algebraic sense. And so I'm just going to explain that kind of slowly. And so the first question is, what are the mutable vertices of Q? And the answer is, well, we're allowed to flip these diagonals, so every diagonal is supposed to give me a vertex of Q. The answer is diagonals. And okay, now the second question is, what are the frozen vertices of Q? And well, the answer to that is the answer to that is the sides of my n-gon. So on each side, I'm going to put a frozen vertex. I'm gonna box frozen vertices. Okay. Now is a good time to guess what are these labels in the extended cluster. And as I already gave you a hint, these are, so x tilde are just the corresponding Plucker coordinates. So you kind of label every side or diagonal connects some I to some j, so you label it by Pij. There's P12, P23, etc. That's your extended cluster. P13, P14, P46. And the only kind of the last non-trivial step is you want to guess the rule for the edges of Q. Edges of Q. And so how do you guess the edges? I mean, you can just draw any edges. And the answer is that these edges have to be such that this mutation rule that's for any quiver right here is supposed to correspond to the Ptolemy theorem, right? There's it's supposed to, so mutation is supposed to give you the three-term Plucker relation. P13, well, let me write it in general. PAC, PBD is equal to PAB, PCD plus PAD, PBC. And in this case, right, so you look at, let's say you look at this quadrilateral here. Yeah, so by the way, if you want to guess, then pause right here and then think about what the arrows should be. Anyway, you choose some quadrilateral. Let's say I choose 1, 2, 3, 4. And then if I want to flip this diagonal P13, then it's going to change according to this rule. So one of the products is going to be P23 times P14, and the other one is going to be P12 times P34. Right, so I'm supposed to have outgoing arrows or incoming, well, let's say incoming arrows from these two vertices and outgoing arrows into these two vertices. And I have to do it for every quadrilateral. So for example, for this quadrilateral, I already have an outgoing arrow here, so the other one is gonna go here to P46. And then the incoming arrows are gonna be from these two sides. And finally, in the last quadrilateral, I'm going to do something like this. And so the combinatorial rule, as you can kind of see, I mean, as I said, I'm removing all the arrows between frozen variables, but you can actually, if you add these extra arrows between the frozen variables, then you're going to see that inside of each triangle of my triangulation, I have a clockwise oriented triangle in the quiver. So every triangle is oriented clockwise. So the rule for the edges of Q is just, I'm going to insert a clockwise triangle inside each triangle of T. And then, of course, I'm going to remove the arrows between frozen variables, between frozen vertices. All right. And so now let me try to apply a mutation. So let's say I choose some vertex. Let's say I choose this vertex P13. And so I'm going to mutate. I'm going to apply mutation mu3 to this, sorry, not mu3, but let's say mu P13 to this seed here. And the point is that mutation is supposed to correspond to flip in the diagonal. But now, so I have this quiver in blue, so first I'm going to mutate the quiver. And again, the recipe is shown here. So let me try to copy the same quiver. And so I'm mutating this vertex right here. So let me try to erase all that stuff that's adjacent to this vertex and preserve the rest. And now, so the first step is telling me to introduce a shortcut for every path of length 2. So in this case in this case I have 2 incoming arrows and 2 outgoing arrows, so I'm going to introduce 4 shortcuts. For every pair, incoming, outgoing, I'm going to create a shortcut. For now, I'm going to keep the arrows between frozen vertices temporarily. So 4 shortcuts. Now let me do them in red. 4 shortcuts are going to look like this. And then the other step is I'm going to have to reverse all arrows which are incident to my vertex. Okay, let me do that. I reverse these arrows. And now finally the last step is I'm gonna erase these double edges that I have created along the way. So there's only a single double edge, which is these 2 arrows are pointing in opposite directions. So I'm going to erase these 2 arrows, but let me also erase the arrows which point between frozen vertices. So I'm going to erase this one and this one. And so now the last step is I'm going to draw the, originally I had the diagonal from 1 to 3, but then I'm going to flip it for the diagonal from 2 to 4. So 2, 4 is my new diagonal, and you can see that what has happened is that I got these new rectangles, and then inside of each of them I have this clockwise triangle again. So this rule of assigning clockwise triangles to each triangle of my triangulation, somehow it is, when you apply a flip, you get another quiver which corresponds to the flipped triangulation by the same rule. And finally, if I wanna compute the kind of, so there is going to be a new variable, x prime, that's assigned to the seed according to the mutation procedure. And so let me label that variable by p24. And so p24 is obtained as a fraction, right? Originally I had p13 here, so I'm going to put that in the denominator, p13, and then the outgoing arrows were, well, the incoming arrows were p23 and p14, so that's one product, p14 times p23, and the other product is p34 times p12. So then that's exactly the three-term Flickr relation. Is it? Yeah, exactly this relation. So the point is that this machinery of cluster algebras in this case exactly gives me the same combinatorics and the same algebra as we originally kind of I explained for the Grossmanian. All right. Now let me try to do another example. This was towards the end of the lecture, so I had like 2 minutes left, and your homework for the next lecture is to try to understand what happens for the case of wiring diagrams. So if I draw some wiring diagram, something like this, one, two, three, four. Then again, well, you can ask all the same questions, like what are the vertices of the quiver, which ones are frozen, and what are the edges, and what is the extended cluster. And so, as we discussed in class, the vertices, so the vertices of Q are just the regions of my wiring diagram, and the mutable vertices they correspond to interior regions. And so let me draw, these are all vertices which are frozen, so I'm going to box these. But then the interior ones are mutable. So that's the easy part, and then you can also kind of guess that you label them by flag minors, but then the arrows between these vertices are supposed to somehow correspond to the way these braid moves change my flag minors. So kind of the homework question is try to guess how to draw arrows in this quiver so that algebraic and combinatorics work together when you apply braid moves. And so that's it. See you on Friday.